Good morning, ECE 108. So today we're going to go through Lecture 5, where we will continue discussing various proof techniques. In particular, we're going to cover the contrapositive, proof by construction, and proof by counterexample. This will be followed by a short discussion of how to prove and disprove quantified statements. So without further ado, let's jump into it. So proof by contrapositive. Sometimes the previous methods don't, quote, work. I spend forever trying to use them to prove a given statement, and I can't get it to work. Well, recall that A implies B is equivalent to not B implies not A. So we can use this to prove things. So here we have a meme where you can look at this at your own leisure. So let's go through an example of proof by contrapositive. Let x be an integer. If x squared plus 4x minus 2 is odd, then x is odd. So before I try to prove this, let's formally define what I mean by odd. You should know, but just for completion. Recall that an odd integer is an integer of the form 2n plus 1, where n is an integer. Okay, so let's try to prove this directly. So if I try to do this, I first need to start with the assumption that x squared plus 4x minus 2 is odd. So what does this assumption tell me? That tells me that there exists an n in z, so an integer, such that x squared plus 4x minus 2 is equal to this 2n plus 1. So now what do I do from here? Well, ultimately I wanted to prove that x is odd, so let's unpack that definition. So I need to use this statement here to conclude somehow that there exists an m in z such that x is equal to 2m plus 1. So how could I do this? Well, I have an equation that involves x. Let's solve it for x. So applying the quadratic formula, I see that x is equal to negative 2 plus or minus the square root of 2n plus 7. So again, I started with something with the integers, and when I take square roots of things, I end up with real numbers. Thus, trying to use this technique brings me outside of the integers, which is kind of a sign that things are going wrong. Secondly, how am I supposed to show that this thing is of the form 2m plus 1, where m is an integer? I can't really do that. So now let's instead consider the contrapositive. So what would the contrapositive of this statement be? So pause the video and take a second to get some good practice. Okay, so the contrapositive is if x is not odd, so if x is even, then this expression here is not odd, so this expression is even. Let's try proving this. Well, if x is even, then that tells me that there exists an n in z such that x is equal to 2n. So now what is our goal? Our goal is to show that there exists an m in z such that this expression here on the left-hand side is equal to 2m. How could I go about doing this? Well, I know by assumption that x is equal to 2n, so let's just plug in 2n into this expression for x. If I do that, I get this expression here is simply equal to 4n squared plus 8n minus 2, and out of all of this, I can factor out a 2. Thus, m is simply going to be equal to this thing in parentheses. And further, since this thing in parentheses here is an integer, I'm done. I've proven the statement. So here you can see where proving the contrapositive instead of the original statement can make things dramatically easier for some problems. Now let's look at another example of proof by the contrapositive. So prove that for all a and b and R, if ab is irrational, then a is irrational or b is irrational. So if I were to attempt a direct proof, do you have any ideas on how I would go forward? Well, I'd have to assume that AB is irrational, and then I would have to prove that I couldn't factor that number into the product of two numbers that were rational. Well, I don't even know how to even begin proving that. So instead, let's look at the contrapositive. So again, pause the video and see if you can come up with the contrapositive is on your own. Okay, so what would the contrapositive be? Well, it would be for all a and b and R, if not a is irrational or b is irrational, then AB is rational, right? The opposite of irrational is rational. Okay, so how do I negate this first statement? Well, I can notice that this statement is of the form not A or B. So to negate these type of statements, I use De Morgan's law. So applying De Morgan's law would be not A and not B. So if I use this rule to simplify this negation, I would have for all a and b and r. If a and b are rational, then ab is rational. Okay, so now can I prove this? Well, the answer is yes, but first I really need to define what I mean by rational numbers. So here, note that a rational number is a number of this form, a divided by b, where a and b are integers and b is not equal to 0. Okay, so with this in mind, how would I prove this? Well, I first assume that a and b are rational, and doing that means I have to assume that there exists an a1 and a2 and a b1 and b2 in z, such that, and this s dot t dot is short for such that, you can feel free to use it, but such that a is equal to a1 divided by a2 and b is equal to b1 divided by b2. So notice that I didn't explicitly say that a2 and b2 are not equal to 0. In a formal proof, you'd want to handle that case, but for the purposes of this rough work, I'm not going to do that extra step. I do it on the next slide, so keep that in mind. Okay, so now what do I need to do? Well, I have this form for a and this form for b. Ultimately, I want to show that AB is rational, right? So let's take A and multiply it by B. So AB is equal to the product of these two rational numbers. I know how to multiply fractions. That's simply A1, B1 divided by A2, B2. And this is of the form of a rational number, so AB is rational. Again, I need to be a bit more careful with this term here to make sure I'm not dividing by 0, but I do that in the next slide. Now, some assigned reading for the contrapositive. I want you to read this formal proof for the statement on the previous slide. So notice here, I explicitly state that these terms are non-zero, and I do mention that this product here is not 0. In addition to this formal proof, I want you to read the proof of claim 7 on page 23 of the course notes. Now let's go on to proof by construction. So if I'm asked to prove the existence of something, why don't I just build an example to say, hey, here it is. So if I were to memify this idea, this is how I would memify it. Okay, so let's look at a couple examples. Prove that there exists a real solution to this equation, x squared plus ax plus 1 is equal to 0, for a squared is greater than or equal to 4. So how would I do this? Well, I know how to solve equations of this form. That's just the quadratic equation. So let's do that. So the quadratic formula tells me that the roots of this quadratic equation here are simply going to be x is equal to negative a plus or minus the square root of a squared minus 4 all over 2. So now I'm concerned about the existence of a real solution. So I can ask myself, when are these solutions for x real? Well, these solutions are going to be real precisely when the thing under the square root, so this term here, is positive. So the roots are real whenever a squared minus 4 is greater than or equal to 0. So I can rearrange this to simply be a squared is greater than or equal to 4, which is exactly what I wanted to prove. Thus, x is equal to this is one particular real solution to this equation for a squared is greater than or equal to 4, and that was by construction. So notice that here I just used plus instead of plus or minus. That's simply because I only need one solution. I don't need the two, and it's not true to say that I have two real solutions, because if a squared is equal to 4 exactly, then I only have one solution. So by taking just simply the positive root or the negative root, I'm just being a little bit more precise there. I'm going to give you some assigned reading for proof by construction. In particular, read the proof for claim 8 on page 23. Now we have another proof technique, proof by counterexample. So if I gave you a universally quantified proposition and asked you to show that it's not true, one way to do this is simply find a counterexample. So again, here's a meme for this. At the exam, prove that the statement is wrong, present a counterexample. So let's look at a few examples of this. So prove or disprove the following propositions. For all real numbers x squared plus 12x minus 1 is greater than 0. Well, if I look at this for a while, or maybe even plot the function, you can notice that it's not always positive. So in particular, when x is equal to 0, this thing is equal to minus 1, which is less than 0, thus the statement is false because I've given a counterexample. Another example. For every positive integer n squared plus 13 is not a perfect square. So here I can just plug in various values and see if it's a perfect square, and for instance, 6 is a counterexample. Or here, prove for every positive integer n that this thing is not a perfect square. Well, I could pick this number as a counterexample. Again, in all three of these cases, there are multiple counterexamples that work. Sometimes that's not the case, but I just picked this large number here to show that there are multiple counterexamples that you can use. Okay, so you noticed here that proofs by counterexample can be really short. You just specify a counterexample. This leads to some fun historical big brain moments, if you will. So let's examine one of these. In 1796, Euler proposed that at least n-th powers are required to sum to an nth power when n is greater than 2. So what does this mean? Well, first notice that in this statement, there's a lot of implicit assumptions made. So implicitly, what do I mean by n-th powers? N-th powers of what exactly? So this is really common in literature when people are talking about particular objects for a sufficiently long amount of time. People come up with their own slang and start using shortcuts. Just to save some time, in this course, I want you to explicitly state everything. And this is because at the level of mathematics of this course, it's very good to be precise so that you're making it clear to me that you understand what you mean. Now let's look at an example of what this means to kind of unpack it a little bit. So for n is equal to 3, Euler's proposition implies that there are no integer solutions in m and k such that this expression is true. I need to have at least 3 elements on the left-hand side of the sum to be able to find such integers. Okay, so this problem was unsolved for almost 200 years, when in 1966, a paper showed that this statement was in fact false. So now, 200-year-old unsolved problem. You would think that the people who showed that this was false would have some new mathematics or some like deep philosophical idea behind the sum of nth powers. Well, here's the entire paper. Counterexamples to Euler's conjecture. A direct search on CDC 6600, which was one of the most powerful supercomputers at the time, yielded that this equality holds. In this case, they're examining the n equals 5 case, so for Euler's proposition to hold, you would need to have 5 integers on the left-hand side. They clearly have 4. This is the smallest incidence in which 4 fifth powers sum to a fifth power. It's a counterexample to the conjecture by Euler, and we're done. So that's kind of a mic drop moment there, but this just goes to show that counterexample proofs can be extremely short. So now that we've gone through several methods of proving statements, let's re-examine proving and disproving quantified statements just to make things a bit more concrete and to explicitly state some facts that have been implicitly using here and there throughout the last 2 lectures. So consider the statement of the form, there exist an x and s such that p of x. If I want to prove a statement of this form, all I have to do is find a value of x that is in the set S such that p of x is true. To do this, you can use something like proof by construction. To disprove statements of this form, I can instead prove this universally quantified statement. For all x and s, not p of x. So where did this come from? Why does this work? Well, I know that the original statement, there exists an x and s such that p of x, is false precisely when its negation is true. And I know that the negation of this quantified statement is simply for all x and s, not p of x. So that opens the question, how do I prove statements of this form? So I'm going to answer that on the next slide by proving statements of this form where instead of having not p of x, I just have p of x. But the technique that I'll talk about there carries over for this case. Okay, now let's consider statements of the form for all x and s, p of x. To prove statements of this form, we need to first start by picking a representative element x from the set S. So this is not any particular element of the set S, but it's an arbitrary element of the set S. So for instance, if S was the real numbers, you couldn't just pick, say, x is equal to 1 and show that it's true for that case. You need to show that it holds for all real numbers. So now, after I've done that, I need to show that the open statement p of x is true for our representative by using properties that all of the elements of S have. So for instance, if x was, say, an odd integer, I could pick an arbitrary odd integer, and then I could use the property that x would be, say, equal to 2n plus 1 for some integer n. And I would use that fact to prove the proposition. So I've already done this in a few of the examples, so a good exercise would be to go back, look at those examples, and verify that, hey, yeah, that's what he did. So here, in proving these statements, I might use case analysis or many of the other techniques that I discussed before. So in conclusion, you cannot prove a quantified statement by finding a particular value for x. It needs to be true for all of the values of x. Thus, why we say for all, right? Okay, so the next question I could ask is, how do I disprove statements of this form? Well, similar to on the previous slide, I prove the negation. So to disprove statements of this form, I instead prove that there exists an x in S such that not p of x is true. Now this has a name. This is just finding a counterexample. So again, we did that previously. Okay, so these last two slides don't really introduce anything fundamentally new, but when you are working on trying to prove or disprove a quantified statement, do keep both of these slides in mind because it gives you the general idea of what you really need to do to prove the statement. Okay, so now just a couple memes at the end to think about, just to make your day a little bit more fun, maybe. And that is it for this lecture.